Okay, so for the first question on your FRQ, so looking at 1A, so what I'm going to do is go through each one and kind of talk through what were some common mistakes, as well as what the right answer should be and how the points were distributed. So take notes on the ones that you missed so I can help you in doing the corrections correctly. Now, it's important to recognize as you look at your FRQ score to remember that, number one, some of them are only out of 1 point. So some of you were often really close to the right answer, but since it was only out of 1 point, you got 0 out of 1 because you weren't all the way there. But recognize the positives in the things that you did, as well as there are some misconceptions that we need to fix. So I'll be hitting on those once again, so make sure if you did have a misconception that we get those fixed. Because remember, the big picture is we just want to understand these things by the big AP test at the end of the year. Okay, let's go ahead and get started. So number 1A says, identify a Bronsted-Lowry conjugate acid-base pair in the reaction. Clearly label which is the acid and which is the base. So technically there's 2 conjugate pairs and you just had to pick one. So if you picked the acid as the one that you labeled as the acid, so if you said that, get a darker one. So if you said CH3CH2COOH was our acid, then you should have said that the conjugate base was CH3CH2COO minus. This is out of 1 point, so you had to have both of them clearly labeled correctly to get the point. Now you could have also gotten the point, so that's one option, or we could have said that the base was H2O and its conjugate acid was H3O plus. So one of these answers would have got you the correct. Now some people listed both, but they didn't label the pairs, and that's a key thing of recognizing, hey, this is the acid, this is its conjugate base. So you have to signify the relationship between the two. Okay, B says, determine the value of Ka for propanoic acid at 25 degrees Celsius. So a lot of you recognize that you knew what Ka was, which is good. So this is our equation up there. The expression for Ka is products over reactants, so it would be the concentration of CH3, CH2, COO minus times by H3O plus over our acid. And then since water is a pure liquid, it's not included in the equilibrium expression. So to find Ka, I need these values at equilibrium. So the next thing is, a lot of you did recognize that this is a rice chart idea where I saw some common mistakes. Just bringing the equation down, I'm going to leave out water. So one of the common mistakes I saw is a lot of people recognize that this pH value right here was important to us. Okay, because a pH tells us information about a solution. What a pH tells us is a pH is directly related to the H plus concentration. So to find the H plus, if we take, so the pH was 2.79. So if we take 10 to the negative 2.79, so we're inversing along, that answer, which was 1.6 times 10 to the negative 3, a lot of you circled this as your final answer, but this is not Ka. This value is the amount of H plus in our system. So this tells us how much H plus we have. Now, if we think through our rice chart here, once again, so this was 0.2, right? Yeah, 0.2 molar. These would have started at 0. The other thing that threw a lot of you off in setting up your rice chart is you use X's. But if you're trying to find Ka, you can't use X's because that's too many variables to solve for it. The reason why we don't have to use X's is because of this. This tells us the amount of H3O plus at equilibrium. So this is this. Well, and then since it's a 1-to-1 ratio, right, that means this one increased by that much, which means this one also increased by that much, making them the same value at equilibrium. And then this one would have decreased by that much. Now, technically, we could do this, but once again, it's so small, it's kind of that idea of how x gets assumed away. So when we plug it into the expression to solve for Ka, you end up with 1.6 times 10 to the negative 3, and they're the same, so I'm going to say squared because it's this times this, over 0.2. And then when you plug it into a calculator, you get an answer of 1.3 times 10 to the negative 5. And that is the final answer. Now, where's some points? So this is where 3 points is how it was graded. Obviously, if you got the right answer, you got all 3 points. You may have gotten some partial points if you found this value and you recognized it was H+, I gave you a point. Sorry, if you said this was Ka, you didn't get a point for that. And then the other point was for plugging it into the Ka expression correctly. Okay, so there is part B. Okay, so for part C, we're given these statements and we have to determine if they're true or false and then explain your reasoning. So on our test, they were both worth 1 point. So you had to have the right claim and then also the right explanation to get any points for it. Because some of you had a good claim, but your explanation wasn't there, so you didn't get the point. Okay, so for part 1, it says the pH of a solution prepared by mixing 50 mils of a sample of 0.2 molar propanoic acid with 50 milliliter sample of 0.2 molar sodium hydroxide is 7. And the claim to this is that the answer is false. Let's first talk about a common one quite a few people put who said it was true. A lot of people claimed, well, these two things are being neutralized, right? Your propanoic acid and your sodium hydroxide, acid and base, when they react, they neutralize, which is true. They would both be completely neutralized. That is a true statement, but where we're off in the fact is that what happens when something is a weak and a strong in how they get neutralized. They're still neutralized, but it's important to recognize that neutralization doesn't exactly mean 7 on the pH scale. A neutralization reaction is simply when an acid reacts with a base. They only can become neutral if they make a neutral solution, meaning a pH of 7. So the correct reasoning to this, I'm going to write an equation to hopefully help, is that when you have a weak acid, so we have our CH3, CH2, COOH, reacting with our, I'm just going to do the OH minus of the sodium hydroxide because that's the main point. When these two substances react, I have equal amounts of both, right? 0.2, 0.2. They, in a sense, are both gone. But what they make in the end, so this will donate its H, so we get H2O plus CH3, CH2, COO minus. So because in the process of neutralizing the weak acid and the strong base, in that process we have made a weak base. Because the conjugate of this weak acid is a weak base. And so because we now have a weak base floating around, the pH of my solution would actually be greater than 7. Both of these are gone, that is true, but they make a weak base in the process. Okay? All right, part 2 says, if the pH of hydrochloric acid solution is the same as the pH of a propanoic acid solution, then the molar concentrations of the hydrochloric acid must be less than the molar concentration of the propanoic acid solution. Now, I had a hard time grading this one because a lot of you were on the right track and I was trying to decide where to draw the line, and I just had to go off what the AP answer key says, because once again, I'm trying to train you to make answers that they're going to accept as valid. Okay, so don't be personally offended if you're like, I pretty much have that. Okay, keep in mind that I mark it wrong because I'm trying to help you. Okay, it would save me so much hassle to give you the points. But if it's not quite there, I want to make sure we get it there. So first off, the claim to this is the statement is true. It is true that if they are at the same pH, then the concentration of hydrochloric acid must be less. Now, first off, let's break this down. So same pH means same H plus concentration. That's, if something has the same pH, it has the same amount of H plus floating around. So the reason why hydrochloric acid must be less then is because since it is a strong acid, and strong acids ionize completely, and weak acids only ionize somewhat, we must have less of the strong one than we do of the weak one. So the part that some of you missed in your explanation was you simply said statements like, oh, it's true because hydrochloric acid is strong and propanoic acid is weak, period. That's a true sentence, but it doesn't quite show your understanding of why. Like, why is it? And you'll see, probably laugh about it, but a lot of you can see next to that question, if you missed it, I wrote the word why. Like, why is it that the strong one has to be less than the weak one? So you need to make sure you included something along the lines of understanding that it's because the strong one breaks apart all the way and the weak one does not. It doesn't mean your answer needs to be that much longer. Just adding in those words that define what strong and weak mean are important to show your understanding to the grader. Otherwise, it looks almost like a memorization fact, that this is just true because someone told me it is and not that I actually understand why it is. So remember with all of your FRQs to focus on making sure your answer clearly shows the understanding to what you're trying to achieve. Okay, part D was worth 2 points. We're trying to, so it gives us this information of a titration that we're doing, and we're trying to determine the molarity of our unknown. Whenever you're trying to find the molarity of an unknown in dealing with the titration, my go-to is M1V1 equals M2V2. Now, in the 2 points of this problem, M1V1 equals M2V2, I gave 1 point if you tried using this, and then the second point is for getting it done correctly. So what we know, so we're trying to calculate the molarity of our propanoic acid solution. So just, it doesn't matter what side, but let's just say this is going to be my acid side, and this will be my base. So I'm trying to find M2, so I leave that as is. It tells me that we use 25 milliliters, where is that, right there, 25 milliliters to deliver the propanoic acid. So this would be 25 milliliters. For the base, our concentration is 0.173 molar, and we're timesing it by the volume of the base, so 20.52. So we just plug in what we know. Then we just solve for M2. So we're going to simply divide both sides by 25. Plug that into your calculator, and you should have got an answer of 0.142 as your unknown molarity. And that's it. Okay, so for part E of number 1, this was out of 1 point. So it says the student is asked to redesign the experiment to determine the concentration of a butanoic acid solution instead of propanoic. For butanoic, the value of pKa is 4.83. The student claims that a different indicator will be required to determine the equivalence point of the titration accurately. Based on your response, do you agree with the student's claim and then justify your answer? Now, once again, just a reminder that whenever it's like making a claim, make sure that's the first thing you put in your answer of I agree or I disagree. Don't make the grader be searching to figure out what your opinion is. Make it very clear from the start. A lot of you actually did really good on this question even though you missed part B, which is what it's linked to, but you weren't penalized for it because you had the right logic. So the logic behind this question for picking an indicator, the way we pick an indicator is we compare the pKa of the acid that we're titrating to the pH that we want, or the pH of the equivalence point. So if you take the answer we got from part B, and this is what you would talk about in your justification, get rid of this. So on part B, we got 1.3 times 10 to the negative 5. So if we take the negative log of that, we end up with a pH of 4, or pKa, sorry, of 4.89. And since the pKa of this acid, it's very close to the pKa of our other acid, the indicator should still work, and we don't need a new one. Once again, some of you said you agree with the student because you got part B wrong, so your Ka was different, but you still get the points for part E for the logic there. So once again, don't forget to take advantage of continuing onward even if you think you've done things wrong, because you can still get full points. Okay, number 2 on the FRQ, so is talking about preparing a saturated solution of magnesium fluoride by adding 50 grams of a solid MgF2 and 100 ml of distilled water. We stir until no more solid dissolves, and we assume that the volume didn't change. The saturated solution is analyzed, and it is determined that the F- in the solution is 2.4 times 10 to the negative 3. First thing is to write the chemical equation for the dissolving of solid MgF2 in water. So probably the most common mistake I saw made on this is a lot of people tried to react magnesium fluoride with water. But all we're doing is we're just dissolving a salt. So all it is, I'm going to write right here, so we have MgF2 as a solid, and in water, it's simply going to break apart into its aqueous ions. So we get Mg2 plus and 2F minus. It is an equilibrium system, because that's what it means when something is saturated. I didn't dock you points if you forgot that, but it is only out of 1 point, so if you didn't balance it or some of you missed your charge, you did miss it there. But when it talks about dissolving, it's not reacting with water, it's simply breaking apart. In a sense, if you did put water in the equation, you could just write it above the arrow. You actually don't even need to include it at all, because by showing that they're now aqueous, that shows that they're in water. All right, part B, what I saw a lot of people do on this one, so this one says calculate the number of moles of MgF2 that dissolved. And a lot of you had a good thought, it just didn't get you to where we needed, where you took and said, where did my other markers go? So on part B, you're not alone if you're like, oh, well, I have 50 grams or 0.5 grams of MgF2. So let's just convert that in to moles, right? And you just found the molar mass, times it out. I can't remember what it is. But that's what a lot of people tried to do. But the flaw in that logic is simply this. You're claiming that all of that 0.5 grams dissolved. But when you have a saturated solution, some of it may not have dissolved and it's just still sitting in the bottom as a solid form. So that's where the your logic went off with doing that method. So what we want to focus on is what we actually know about our system once it has dissolved. So the thing that we know is we know how much F- is floating around. So if I take the molarity of my F minus, I can convert that back to see how much MgF2 actually did dissolve. So if I take my volume, so what was my volume here? 100 milliliters. So if I take, so I'm going to change that into liters, so 0.00 liters, and I times that by my 2.4 times 10 to the negative 3 for F minus, sorry, not molarity anymore, this would just be moles. So I'm using my molarity. So molarity is moles per liter. Then I can go from, for every 2 moles of F minus, I have 1 mole of MgF2, right? So that 2-to-1 ratio just came from the balanced equation. And then you plug that in, and we get an answer of 1.2 times 10 to the negative 4. Yep. Moles of MgF2. And that's the final answer. This one was out of 2 points. And the points divided up okay, so if you recognized using the amount of F minus, there's your 1 point, and then the second point is for the correct stoichiometry to get the answer. Okay? All right, C, determine the value of the solubility constant KSP for MgF2. So KSP, let's write, is just like all of our other Ks. I'm going to write it up here in blue, the expression. So KSP is products over reactants. So our products are Mg2 plus and F minus squared. But then since this is a solid, it's not included in my expression, and so that's it. The thing about KSPs is you never have something on the bottom because your KSPs are for dissolving. And so when you dissolve something, it's always a solid. So to find this value, we just need the amount of MgF2 and the amount of F minus at equilibrium. Well, we already have the amount of F minus right here. Told us that in the problem. So now we just need to know how much Mg we have as well. So once again, you can think like a rice chart. You can skip steps if you understand where it's going. But I'll write it out for us. So we have MgF2 right? So this doesn't matter the whole time. So these were 0. The thing that I now know is I already know at equilibrium, I know the value of this is 2.4 times 10 to the negative 3, which means the change had to have been plus 2.4 times 10 to the negative 3. So that would mean that the change of magnesium, now this is where a few people got slipped up because it's a 2-to-1 ratio, would be 1/2 2.4 times 10 to the negative 3. And so then that ends up being 1.2 times 10 to the negative 3. So everything in brown is what I figured out from what the problem gave me. And then we just take these, plug them in up here, making sure to square your F minus, and in the end you get 6.9 times 10 to the negative 9 as your final answer. Once again, I know we have lots of K values, but try to relate them all the same, that it's always a relationship of products to reactants every single time. So then finally part D says to describe one method to increase the solubility of MgF2. So some of you, I think, mixed up a little bit what it means to increase solubility. If I'm increasing the solubility of something, I'm making more of it dissolve. Nothing about speed. Some of you talked about like, oh, grind it up into a powder, stir it. That's not going to make more of it dissolve. That will just make it dissolve faster, but the same amount, right, will still dissolve each time. So there's 3 different options for answers. The whole idea, I erased our equation, but we pretty much, if I want more of it to dissolve, I want to do things that will cause the equilibrium to shift to the product side. Right? So that's the goal with this question. To increase solubility is I need to do things that would make it go this way. So some options are, number 1, if I add more water, that will cause more of it to dissolve, because since we're talking about salt and water, you add more water and more can dissolve. Another thing that some people said and that you can do is heating the substance. Right, that's like our super saturated solution we made in class. If I heat it up, it will force more of it to dissolve. Other options are, some people talk about a common ion, that if I remove one of these substances through some means, I can force more of it to dissolve. On the same note, if I make it an acidic solution, so if I add H+, that will also cause it to dissolve, because that's a way in which this would be pulled out, and so then it would shift more in that direction. That one was worth just 1 point, so pretty much you got it right or you got it wrong. Okay, so finally, question 3. Now there's a slight mistake, and those that you picked up your test yesterday already kind of know this, but parts A and B were not supposed to be on the test. I thought I had cut them out simply because of the fact of time, right, and trying to manage how long, the 30 minutes. But I didn't, obviously, and a lot of you didn't, and I was actually really proud because a lot of you did a really good job on them. So what I decided to do is A and B are going in as extra credit. You won't see them on your actual test score, but there will be a separate score that they go on where you got those points back. So I'll still talk about them because it's obviously, for the end of the year, we need to know how to do it. And you can, if you miss them, you will be allowed, if you want to retake them even, you can get those extra credit points back as well. Okay? So part A, write the expression for the equilibrium constant Kp for the following reaction. So just like we talked about, Kp is products over reactants. So you should have the pressure of NO. And then since there's 2 in the reaction, this gets squared over the pressure of N2 times the pressure of O2. And that's it. Most of you guys did actually a really good job on that relationship. Okay, all right, part B is the student injects the substances into a vessel and the temperature is that. It tells us the initial pressures of the N2 and O2. It then tells us the partial pressure of NO at equilibrium, and we're trying to calculate Kp. One thing I was really proud, a lot of you guys did a great job on this, which this is also a rice chart problem. So it was cool to see that starting to click. Now, the mistake I saw most often made is people just took the values they gave us and plugged them straight in. And they said, oh, well, 0.601, here's N2, and then that, and solved it. The issue is you're plugging initial values into a Kp expression when Kp should be at equilibrium. So that's where we have to have the rice chart to see how they change. So here's our equation. Okay, so it tells us initially we have 6.01 for N2 and 1.61 for O2. And that would have been 0. And then it tells me at equilibrium, it's 0.122. So that's everything the problem gave me. And then the other mistake I saw people made is they had this and then they started adding x's in. You're good. Once I have an end value, I don't need x's because we already know. If we know the start and the end, we can figure out the middle. So the change here, so I'm going to do change in orange, must have been plus 0.122, which means, because it's 2 to 1 to 1, this would have minus by 1/2 of 0.122. Same thing here, like so. We then plug those in, get those answers, and then plug those three things into KP. In the end, if you do it correctly, you should have got an answer of 0.00161 or 1.6 times 10 to the negative 3 as your KP value. So there's number 3, part B. Oh, that one was worth 2 points, and part A was worth 1 point in terms of the bonus. So the bonus points available were 3 points. Okay, part C. It says a student is asked to make a buffer solution with a pH of 3.4 by using a 0.100 molar HNO2 and a 0.00 molar of sodium hydroxide. Part 1 says this was worth 1 point, so you have to have the right explanation and also the equation, because that's what the question states, is to write the net ionic equation, and says it's only 1 point. If you're missing one or the other, you didn't get any. So explain why the addition of our strong base and our weak acid can result in the formation of a buffer, and then include the net ionic equation. So let's start with the net ionic equation. So it's HNO2, so that's our weak acid, plus our sodium hydroxide. Now the overall reaction is they'll trade partners, right? So we'll get H2O, HOH, plus NaNO2. Now to get to the net is we take out the things that are just spectating, right? Now this is a weak acid, so it stays together, so it's HNO2. The strong base, though, splits apart. And then sodium salts also break apart, so this would be Na plus and NO2 minus. So your net ionic equation gets rid of the sodium because it's just spectating the whole thing. And we end up with HNO2 plus OH minus, changing into H2O plus NO2 minus. So that's the equation you need. You didn't have to show these other ones, but that's just the process of how we get there if you can't do it in your head. So now we're trying to justify why this makes a buffer. Now once again, some of you simply just stated kind of a fact and you said, oh, well, a weak acid and a strong base make a buffer. Well, yeah, but you could just memorize that, like, why is it that it creates a buffer? What about this helps us to have that buffer solution that can resist changes in pH? So the key things that you need to recognize here is that in the process, or one thing that also a lot of people claimed is they're like, oh, well, you have an acid that can react and a base that can react, and so there's your buffer. But the truth of the matter is if you look at the problem, is we're adding more acid than we are base. Well, I guess it doesn't tell us our amounts quite yet. Let me double check here, sorry. Okay, well, so here's the idea of what plays the role in a buffer. The thing that plays a role in a buffer is not this. It's the fact that the strong base makes a weak base, and those are your two parts of your buffer solution. Because it's the conjugate base that's made that reacts with any H plus that is added, not the other way around. Because if we did add, it doesn't say it yet, but if we actually added equal amounts of these to our solution, well then that's a titration and we've just lost our acid, and now it's not a buffer at all. So when you make a buffer, you actually want to add more of this than of this, and we'll get to that on the next problem, because we want this and this present in a buffer solution. Okay, for CII, it says determine the volume in milliliters of a 0.1 molar NaOH and the student how much they should add to make a buffer solution with a pH of 3.0, and then justify your answer. So a lot of you recognize the fact that we should be using our Henderson-Hasselbalch equation because we're dealing with a buffer. So you have the pH equals the pKa plus the log of the conjugate base over the acid. Okay, and where I saw the most common mistake or misconception is a lot of people claimed and they said, okay, well, notice that the pH that I want, so I want a pH of 3.4, and my pKa is actually 3.4. So they were saying, oh, well, in that case, these two things must be equal because the log of 1 is 0. So then those would equal each other. And so a lot of people claimed and said, oh, well, you need 100 milliliters of base, so it's equal to the amount of acid. Where you got off is the fact, once again, with a buffer, so let's bring our equation back here. The A minus is not the base, it's the conjugate base that's being made. So if you actually have the same amount of both of these, like we talked about before, that actually HNO2, our acid, would be gone. We wouldn't have the same amount. So if I want, so the goal here, what we need for this to be true, is we need the amount of HA to equal the amount of A minus. So in that case, we need half of this gone, so we need half the amount of base. So that's why the answer is 50 milliliters, and the justification is as follows. That I need equal conjugate to the acid, so I need half the amount of base, so that half of my acid gets neutralized, and then I have the same amount made on the other side, right? Because if this was 100, well, this would decrease by 50, this would decrease by 50, and this would increase by 50, so then we end up with 50 and 50. So equal amounts at the end. Okay, D, let's move on. Okay, so for part D, a second student makes a buffer by dissolving a 0.1 moles of NaNO2 and 100 mils of a 1 molar nitric acid, which of the following, nitrous acid, sorry, which is more resistant in pH when we add a strong acid or a strong base? Was it the second student or the first student? And then justify your answer. So now once again, a lot of you, I got confused because you didn't state a claim. You didn't claim which student you were picking, so I didn't quite understand your answer. Now this is just worth 1 point, so you had to pick the right student and have a right explanation. So the second student is the one that you would want to pick, and it's simply that the second student used a higher concentration. Because this was this was a 1 molar by the second student when the first student only used a 0.1 molar. Greater concentration, greater buffer capacity, and so the buffer lasts longer. Simple as that. Okay, for part E, it says a new buffer is made using our HNO2 as one of the ingredients. A particular representation of a small portion of the buffer is shown in the picture. And then, is the pH of the buffer represented in the diagram greater than, less than, or equal to 3.4? Justify your answer. So this links back to, in a sense, this one, where we found that if the pH was 3.4, so let's bring our Henderson-Hasselbalch back. So pH equals pKa, the log of the base over the acid. Okay? So before, when we wanted the pH to be exactly 3.4, we knew that the A minus needed to equal the HA. Well, now the question is, how has the pH changed? So in our picture here, if you simply just count, So our NO2s, we have 1, 2, 3, 4, 5. And our HNO2s, you end up with 10. So now if you plug these into the relationship, you could think of it in one of two ways. One, we have, so the NO2, so the conjugate base, is greater than the acid that's present. Oh, wrong direction. I mean, it's less than the acid because it's 5 to 10. So if there's less base than there is acid, then the pH must be less than the 3.4. And you actually can justify just using this relationship. You can actually also even plug in 5 over 10 into this equation and actually calculate that the new pH is a 3.1 value. So obviously it's less than the 3.4 that it was before. Now with this video, as I went through the answers, oh, that one was with 2 points, by the way. The breakdown of the points were given, sorry, let me find my paper. Oh, is by saying that it was less than and then having a valid justification. So if you said less than, you got a point, and then you had to justify it correctly for that one. Okay, so once again, if you've gone through this video, it's going to be posted on the website so you can watch it again or go back to the certain parts you need help with, and you can still come talk to me about it, okay? So the point of this video is just to give you what the right answers are, but if you're still confused of how we get there or parts of it, please come ask because I want to make sure I have a good understanding. So use the rest of the class now to work on those corrections. You can take your multiple choice if you're ready. And let's use our time wisely. Multiple choice is due on Tuesday. FRQ is due on Friday.